Okay, I think we can get started. So, welcome all of you to the first of the technical NAG memory lectures. Our lecturer is Professor Atish Dabolkar from ICTP. He is currently the head of the Theoretical Physics Division at ICTP. I will make a formal introduction to him in the evening before the public talk. So, for now, I'll just say that his topic of the lecture is quantum black holes and modular forms. And we'll let Atish
Okay.
go ahead.
Okay, thank you, Sujay. Can you hear me? It's good now. Okay, it's a pleasure to be here. I have many friends here at IISc, but I never visited this place. So thanks for organizing this. Thanks to Sujay for organizing this. So my talk in the evening is about was also about quantum black holes, and it's about Hawking and Ramanujan. It's an encounter between Hawking and Ramanujan. So I was asking Sujay what I should talk about. I could talk about something very recent that I've been doing on localization and things like that and Liouville theory, but he suggested that maybe it would be in line with, since these are NAG memorial lectures, it would be an expansion of my popular talk I will present as a technical seminar. And so some of you might have heard parts of it because this is a subject I have been working on for the last 10 years. And there has been quite a lot of very interesting development. And I think the title of this public lecture really does capture it, and that it really, there is a very interesting connection between Hawking and Ramanujan that one keeps going back to. So quantum black holes and modular forms is sort of, one side is Hawking and the other side is Ramanujan. You can think about it roughly like that. And it has come to play now an interesting role in various other recent developments like wall crossing phenomena, holography, computing quantum corrections to holography. So the same set of ideas have also, since there are students in the audience, I will try to start from the very beginning. So maybe I should ask, what is the background of the audience in the other? I know many other people here, but are you all?
They're not all string theorists.
You're not all string theorists. Okay. Yes.
So many you don't respect the answers.
No. So you're not all string theorists, but all of your students are postdocs. A mix, right? A mix. Okay, then I think I sort of know. I will then really start at the very basic, from a very basic thing, trying to get up to the more advanced topics. So that, okay. Okay, but everybody knows what is a black hole, right? I mean, you have done a course in GR. That everybody has done, right? So, what is the question and what we are interested in, and where has the progress happened in the last few years? So, of course, classical black hole is, is just the solution of Einstein's equation. Schwarzschild solution is the simplest example, but you can consider more general solutions like Reisner-Nordstrom black hole. And the metric is very simple. It's a solution of, okay, in that case, you also have to include, so you start with an action which is Einstein-Maxwell action. And one of the solutions of this is the Reisner-Nordstrom black hole. And the metric is actually very simple. So I'm going to say G equal to H bar is equal to C is equal to 1. The same factor So this is a well-known famous solution. If you put Q equal to 0, this is the Schwarzschild solution. And as you know, it has a very strange causal properties. Namely, if you write down the space-time diagram, there is a singularity. There is a singularity at r equal to 0, but it's space-like, and r is equal to 2m. So I'm not. Let me describe a simpler case. Q equal to 0, r is equal to 2m is the event horizon. So this is just a reminder that all of you know this. So the diagram is to be understood as there is a time direction here and there is a r direction here. So the observer sitting far away at r, this is r going to infinity. Sorry, time is going up and r is here. So r is going to infinity. You're basically like in flat space. You're going, r goes to infinity. You're in flat space. The observer is going straight up. Constant r corresponds to just going straight up. But at r is equal to 2m, it becomes a null line. And the definition of the event horizon is the stationary null surface. So it's kind of a peculiar, it's stationary because it doesn't depend on time, but it is null at the same time, it's moving at the speed of light. And it's a peculiarity of this metric. And that's a kind of a technical definition of an event horizon. Of course, intuitively you think of it as just a black hole. This is the picture of a black hole. And r is equal to 2m is this surface of the black hole, area. And at each point there is a sphere. I mean, I suppress the sphere, there is a d omega 2 square. So this point is clear, right? From this we can move on to semi-classical black holes. So semi-classical means you take the black hole to be classical, but you quantize some field in the background of this black hole. And it was clear that the black hole is very paradoxical already from many points of view. One of the first paradoxes was, of course, its second law of thermodynamics is violated. So, a classical black hole violates the second law of thermodynamics. Why? Because you can take a bucket of hot water and throw all the entropy into the black hole, and then you would lose the entropy for the outside world. So you can decrease the entropy of the outside world as much as you want. And so the second law of thermodynamics, which says that delta S is equal to. So only way to avoid this is if the black hole has entropy. So this implied, this was the Bekenstein's argument. But then, using the first law, implies that the black hole has temperature. Because remember, first law is dE is equal to TdS for fixed volume. So if you have E is just the mass of the black hole. If it has entropy, then it also must have temperature. But since an event horizon is a one-way surface, in that, because it's stationary and null, once you cross the event horizon, you cannot escape to infinity because you cannot travel faster than the speed of light. So therefore, how can a black hole have temperature? Because if it has temperature, then by Stefan-Boltzmann law it should radiate. And so this implies Hawking temperature. So it's a kind of a series of paradoxes, and if you try to resolve the first paradox of violation of the second law of thermodynamics, you are led to a paradox with the first law of thermodynamics. And if you try to solve that, you are led to this notion of a temperature, and then the entropy of a black hole is area upon 4. So in this case, the area is just 4 pi times the area of the horizon. For a Schwarzschild black hole, the horizon is just 2m. Right? That's where something funny happens to the metric. So then that leads to the third paradox. There is a paradox with Boltzmann relation. But Boltzmann told you that if something has entropy, it must have an interpretation in terms of the number of states, the degeneracy of the states, say with mass m. And since a black hole is really like a hole in space-time, how do you account for its So notice that this is a very, very beautiful and very important relation, and I don't think its implications have been fully exploited, because it also has led to the notion of holography, which I will come to. And it has become a huge field just trying to understand what does entropy of a black hole mean. And so I want you to appreciate that it's not just it's a very, very important formula for anybody interested in quantum gravity, or generally, I think it's one of the most beautiful formulas in physics, in theoretical physics, and it's not going to be experimentally verified anytime soon, but it is based on very, very solid physical principles, like the second law of thermodynamics, quantization of fields, general relativity, quantum mechanics. So there is no question that this formula is right. No serious physicist doubts that this formula is right. And why is it so important? Because if you remember, I want you to draw an analogy with, say, people like Maxwell or Gibbs and so on. That in the 19th century, when you could not really observe atoms, Maxwell and Gibbs and, of course, not to forget Boltzmann, it's a very profound idea that this side is macroscopic and this side is microscopic. Right? So, for example, if you believe that this room is made up of atoms, as Boltzmann and people tried to. Now, if you remember, until the 1900s, the atomic hypothesis was not believed by many people. Most of the chemists didn't believe in the atomic hypothesis. And some people say that it drove Boltzmann to commit suicide because of this, but that's not the only reason. But it was not something that we take for granted. And if you think about it, how do we know that this room is made up of atoms? Right? If you cannot observe it under a microscope. So that's the kind of situation we are in string theory or in quantum gravity. We don't have powerful enough accelerators to really do experiments, direct experiments. But nevertheless, if you ask good questions and if you follow, solid ideas, you can make progress, So, and one example is, for example, the atomic hypothesis. The kinetic theory of gases, we take it for granted, right? That there is an ideal gas, right? You do this in your high school or undergraduate physics. And what is the idea? That you basically, suppose you have a room full with some volume V, and if you have n nitrogen molecules in this room with some typical size lambda, which is typically the thermal wavelength of this, then it becomes a counting problem. Calculating the number of microstates for a given energy becomes a counting problem, that in how many ways can I distribute these n particles. There are basically n V divided by lambda cube boxes, and the number of ways is you can just calculate. You can put one here, then you can, if it's dilute gas, then two here. So basically the number of V is d of n is going to be V of lambda cube to the power n. But you know that this formula is wrong. And this you must have studied in your statistical mechanics course, the famous Gibbs paradox. Why is this formula wrong? Because the particles are identical. Now, to define what is an identical particle is a very subtle thing. The particle is really strictly identical. It's not like a cricket ball which looks like another cricket ball, but there could be a little dot on one at which. Identical particles is really identical particles, and to really understand identical particles requires a spin statistics theorem, quantum field theory. All this was, we are talking about 1860, So this was almost 60, 70 years in future. But Gibbs, just by thinking about thermodynamics, figured out that you have to put an n factorial there. And that then the formula agrees with Boltzmann. Okay, so we sort of want to emulate these masters because we are sort of in a similar situation that we don't know when string theory will be verified or when we will have the final version of quantum gravity, but maybe it's another 50 years in our future. But in the meantime, we would like to not just, search randomly, but look at very solid and strong clues given by semi-classical quantum field theory. So this is the question about quantum black holes, right? This brings us to the quantum black holes. So what do I mean by quantum black holes? By quantum black holes, I mean that, yes, well,
Bus was late, I'm sorry.
thank you. Well, Professor Mani was my professor in IIT Kanpur when I was an undergrad, and TRG was also there at that time. So following these, so let me just quickly review that we sort of just saw that just following basic contradictions with well-established principles of physics, namely second law of thermodynamics requires the black hole to have entropy, first law of thermodynamics requires the black hole to have temperature. Then Boltzmann relation requires the black hole to have some kind of a counting explanation in terms of microstates. So D of the microstates of the black hole. And what do we mean by microstates of a black hole? In statistical mechanics, what you mean is that in your Hilbert space of your theory, if you fixed energy and some other conserved charges, you get some Hilbert subspace with say energy m and some charge q. And typically that Hilbert subspace is finite dimensional, and dimension of that Hilbert subspace is d of m. So to be able to really talk about black hole microstates, you need a complete quantum theory of gravity in which the black hole can be imagined to be a state in a well-defined quantum Hilbert space. And that is where string theory comes into picture. So string theory has been one of the, I would say, one of the most promising candidates for a quantum theory of gravity. And there you have a well-defined notion of a quantum Hilbert space such that a black hole is not a state, but it's still an ensemble of states. So for example, this is like, if you remember from statistical mechanics, this is like the microcanonical ensemble. You fix the energy and the charges, right? And what does an ensemble mean? Ensemble just means a collection of states with those fixed quantum numbers, given energy and given charge. That is an ensemble, right? That more formally it means it's a Hilbert subspace, right? You basically, suppose a Hamiltonian is some operator, you want to look at states which have energy m, and you want to, if there is a charge operator, you want to look at states which have these properties, right? And this defines a Hilbert subspace, right? So, as you see, starting with a simple solution in general relativity and just following thermodynamic reasoning, we are led to a notion of black hole microstates and some notion of quantum Hilbert space of gravity, where we should be able to do some counting in exactly the same way as we did a counting for the entropy of this gas in this room. And why is this so powerful? Why is Boltzmann relation such a deep and important relation? Because it gives you a connection between macrophysics and microphysics. So this counting that you did and putting this n factorial to get rid of the Gibbs paradox, if you now take the logarithm of it, you get some quantity. It is obtained purely by combinatorics, right? We didn't do any physics calculation. I mean, it's a physics calculation, but we did not do any physical experiment. But now you can put a heater in this room and measure the amount of heat that you're adding to this room divided by the temperature, because remember, entropy also has this definition: change in entropy is the heat added divided by the temperature. So that is a macroscopic way of measuring the entropy. And then if your theory is consistent, if your atomic hypothesis is correct, right, if you really believe in atoms, do they explain this entropy or not? That becomes the question. And that was how people in the 19th century, in 1860, people could actually conclude something about the atomic structure of matter, right? They said that matter has a quantum structure, it is made up of atoms, it is made up of identical particles, there are n factorials, all this which was really not possible to really make it precise in those days without quantum field theory and so on, spin statistics theorem. But they had all the right ideas. They had to put some cutoff in the phase space h of order h bar by hand, but they were basically on the right track. And in some sense, string theory is in that kind of a state that we want to use the thermodynamic properties. So this side is thermodynamics, and the other side is statistical mechanics. And so we want to use the thermodynamic properties of a black hole to learn about the statistical mechanical properties of the black hole. And by that, what we aim to do is to learn something about the quantum structure of gravity and quantum space-time. So this is a kind of a principled approach. Even if you cannot do an experiment, we can, in the same way that one could, because this relation is universal and is well defined, one can learn something about the quantum structure of space-time without having to do, even if you're not able to do an experiment. And in particular, suppose for this room, it turned out that when you took the log of this quantity and it did not agree with the entropy, then you would know that atomic hypothesis is simply wrong, or your ideal gas model of the gas in this room is not right. And that's the kind of thing that we want to do in string theory, that even though we cannot do an experiment, we can actually try to prove the theory wrong. I mean, that's always a good strategy, that if you believe in something, you try to prove it wrong. You try to push it as much as you can to prove it wrong. And if you still succeed, if you don't succeed, that gives you some more confidence about the theory. And it will turn out that actually string theory passes some of these states in a rather spectacular way. I mean, and that's sort of part of the reason why many physicists tend to take it seriously, even though, because it sort of works in a very complicated way, but finally the answers agree in a quite impressive way. And in that story, modular forms play a role. So this is where Ramanujan comes into the picture. So that is sort of now the first part of my talk was to explain what are quantum black holes. Now I'm going to explain to you where modular forms come into this story. Okay, so are there?
You are considering ensemble.
Yes.
How do you arrive at that? Black hole is a single object.
Yes, black hole appears like a single object.
Yes, appears as a single object.
Yes.
But we assume it is ensemble structure.
Yes, because it has entropy. If it was a single object, it would not have an entropy.
this can be look like a single object. And
But single object does not have entropy. If it was an elementary particle, it would have a zero entropy.
if you can consider a single object on which there are forces, then there are three kinds of forces. You can have gradient force times linear displacement plus surface force times the surface area, and third volume force times volume.
Yes.
And therefore, if you compare that topological picture with first law of thermodynamics, you will identify area with.
Yeah, but you know, in every system that we know, for example, which has entropy, it is always consists of like entropy in this room, right? Or a hot star. If you look at a hot star is not a. It is a single object, but it is made up of lot of micro constituents. Yes. Yes. So in the case of black hole, we will find in string theory there is a particle picture. There is a kind of a constituent picture of the black hole which I'll describe.
What I'm saying that if you go by geometry, you get
Yes.
area proportional to this.
Yes. The question is this part.
Cohomology will tell you that that is here.
Okay. Maybe we.
Cohomology of the sphere.
Well, I think the cohomology will not explain the entropy of the black hole.
This is what I say that if you have a force acting on one single object, then you write it as a gradient force.
Yeah, but see, entropy has nothing to do with forces, right? Entropy.
When you compare it with the thermodynamics, you get the area proportional to entropy.
Okay, maybe we can discuss this afterwards. Let me now explain the other part of the story, namely modular forms. So the important thing about entropy, as I have explained here, is that nowhere did I have to talk about dynamics, right? Whether I'm talking about, it's just about the structure of the Hilbert space, the dimension of the Hilbert space, right? So that's why entropy is a kind of a subtle concept, right? There is no operator corresponding to the entropy. There is no single operator whose eigenvalue is the entropy. Entropy tells you how big is your Hilbert space for these quantum numbers. And that's a completely kinematic information, if you like. I mean, of course, kinematic to the extent you still have to solve. You have to know what is your Hilbert space of the theory. But once you know the Hilbert space of the theory, you just have to, it's a counting problem. And that's where the modular forms come into picture. So, calculating d of m in general reduces to a counting problem.
What I don't understand. What does it mean? Unless you assume there are all these states are there.
Yes. So I will explain to you that these states are actually there for the black hole.
Artificially, you know.
Yes.
No, I think we should postpone this.
Yeah. Okay. So, if you want to explain the entropy using the Boltzmann relation, then we have to be able to compute d of m in some way. And computation of d of m is generically a hard problem, but as I said, fundamentally the problem is about computing the dimension of some Hilbert space. Right? So it's a well-defined problem, okay? Of course, what that Hilbert space is very complicated. For example, it can be some bound state of some objects, right? And solving the bound state problem is typically very hard. You need to count how many bound states are there, given so many particles, right? So that kind of problem is not generically easy to solve. But fundamentally, it is just a counting problem. And that is where the modular forms come into picture. And one of the most successful early results on this goes back to also work of Sen and then followed by Strominger-Waffa. Who looked at some very specific black holes which are called the extremal Reisner-Nordstrom black holes. for which the mass is equal to the charge. So mass is proportional to the charge. For these extremal black holes, nevertheless, it has entropy. And you can calculate the entropy. And this limit is easy to deal conceptually, practically, but conceptually, one can do similar calculation even if the mass is not equal to the charge. There are many advantages in taking mass is equal to the charge, and one of them has to do with supersymmetry. But I want to emphasize that supersymmetry, it's not, the problem that we are interested in is generic. The problem is that explain the entropy of a black hole, just like you explain the entropy of this gas in this room, right? By some fundamental microscopic structure. And in string theory, a certain class of black holes with charge Q, for example, their entropy then depends only on the charge, and it goes as, if I remember correctly, pi times square root of Q cube. Okay, for some particular black hole that Strominger and Waffa considered. This was already back in 1996. And some of the black holes that Ashok considered, the entropy goes as, there are two types of charge. This is like Q1 square minus Q2 square. Okay, so there are very explicit formulas that you can calculate for this entropy. And okay, let me just focus on this one.
Q
And-
is compulsory.
Sorry?
Q is compulsory.
Yeah, Q is non-zero. And then the question becomes, does your quantum Hilbert space of your theory have sufficient number of states such that, can you calculate D of Q? And these people were able to calculate it using modular forms and similar techniques. And quite beautifully, it's a quite complicated actually calculation.
So the first expression is not by count. First expression by
First expression is just from is equal to area upon 4. From the geometry. So the first expression is easy. You just calculate, look at a black hole with the charges, you take a certain limit and you calculate that.
about 3/2. That's like m to the power 3/2.
Yeah, so this is actually this particular black hole is in 5 dimensions and it's an extremal black hole, so their powers are a bit different. But similar things have been done for 4 dimensions, so I'm just taking the simplest example that was considered first. But the main point is that you just have to calculate area upon 4. You look at the solution, it's a very simple, relatively simple solution, like Rasmussen-Nordstrom solution. You take its limit, you calculate the area of the horizon, and you get an answer. And that answer, you just get from geometry. It's like thermodynamics. The highly non-trivial thing is that, does that thermodynamics have some statistical underpinning, right? Every thermodynamics, that way I've learned from Boltzmann, that wherever you get thermodynamic quantities, they make sense only if you can give them statistical interpretation. They should have a statistical interpretation. And Strominger and Waffa and Sen basically were successful in giving us statistical interpretations of this. But there have been a lot of subsequent developments, and which is what I want to maybe describe, and where some of these connections with modular forms become more and more important. First is to compute quantum corrections.
Again, thermodynamics, doesn't charge arise?
Sorry?
Charge in which
Yes, you can consider a grand canonical ensemble, then it has a charge. You can consider an ensemble with some charge, which is a grand canonical ensemble. So now we want to compute corrections to the S of Q, which is in general for a black hole. What do we mean by that? Area upon 4 is actually only the leading answer to some quantity. And generically you expect all kinds of corrections to it with some coefficient A log of area plus B upon A square or B upon A plus C upon A square and so on. And sometimes you can even have non-perturbative corrections. And the question is, can we calculate all these corrections first of all? Can we even give a definition of these corrections? And this was done by Wald, who is again the general relativist for his own reason. He gave a definition, a generalization of the Bekenstein, this area formula of Hawking and Bekenstein, so that you can calculate these kinds of corrections. He didn't have a good definition for this log piece, that I will come to later. But the point is that it's once again a well-defined question, can we compute these corrections? And then the second question is, can D of Q agree with exponential of this? Now, when area is large, this formula is valid, right? Large area. So by the way, area has dimensions of length square, but here is a dimensionless quantity because we are measuring it in the Planck unit, right? So area is a dimensionless quantity measured in Planck units. So as long as the area is much bigger than the Planck length square, this formula is a good approximation. But as you make the black hole smaller and smaller, all these corrections are going to be important. And then the question is, can we compute those corrections systematically?
Does that mean you put more and more information into the black hole somehow? Suppose more information is lost in the black hole, so area is going to change for the black hole.
Okay, so there is a kind of information theoretic connection which has to do with the information loss problem. I will not get into it because it's a completely different subject altogether. But it's a very interesting question because it appears that a black hole loses information because it's not S matrix is not unitary. You can collapse, you can take two particles and scatter them, and the radiation is always thermal. So whether you form the black hole by collapsing two Encyclopedia Britannica volume 1 or two Encyclopedia Britannica volume 2, the outgoing radiation will always look the same. So you apparently have lost the information about which volume of the encyclopedia you have dropped into the black hole. So that information loss paradox is a very subtle and very important. There has been some important progress on that front as well, but that's a completely different topic. But I would say that this question is not resolved yet. So information loss problem is not really fully understood in string theory. Whereas the origin of the entropy of a black hole in terms of some counting of microstates is extremely well understood in some of these examples. And to the extent that it's quite striking that I'll tell you, the D of Q should be an integer. So if you are really strong enough to calculate all these perturbative and non-perturbative corrections, and you take the exponential of that, since D of Q is a dimension of some Hilbert subspace, that thing should add up to an integer. And that sounds like almost a miracle, right? By adding real numbers, how do you get an integer, right? All these coefficients have to be extremely finely tuned. And amazingly, there are calculations that you can do, very non-trivial calculations, where you calculate these quantities. First of all, as you know, even from your basic course in quantum field theory, going beyond one loop is even you don't do for even in your quantum field theory course, right? In QED, if you have to go to 2 loops, it's already a big mess. And nobody, I think, in this room has probably done a 3-loop calculation, or very few people. And computing non-perturbative corrections is even harder. But it turns out that because of, for these special black holes with m is equal to q, for a class of them, you can actually develop methods using supersymmetry in an important way. So these are kind of toy models, I would say, to the extent that they do not correspond to the real black hole, which does not have a charge. But they capture an important physical question, namely, the property that they share with the real black holes is that they have entropy. So you want to explain that entropy in terms of some counting. And remarkably, for these black holes, you get actually an exact integer in some cases. And that again, once again, is a very beautiful story.
The actions which you have for the velocity A by they are not necessarily geometric.
Yes.
So there is some dynamics in it.
Yes.
And the dynamics can be different in different subjects.
Correct. Yeah, so they are not universal. So that's a very good point. That unlike the area formula, the nice thing about the area formula was that it's kind of completely universal. It doesn't matter whether you are in 5 dimensions, 4 dimensions, 10 dimensions, how many charges you have. The formula is always area upon 4. The subleading corrections actually depend sensitively on which. It's also like in statistical mechanics, right? That if you're computing say specific heat of solid, it depends whether it goes as T to the 4 or goes as T square, or tells you whether phonons are contributing to the entropy or electrons are contributing to the entropy. So the fact that it is not universal is actually good, because then you can learn something about the structure of the theory. And since string theory sort of gives you the whole answer, I mean, you cannot twiddle whatever string theory, I suppose it gives you some particular compactification or particular black hole. Then your calculation framework is completely set. You cannot fudge around. You just go ahead and calculate, and it may happen, it could have happened, that these coefficients are completely off and they don't agree. But and they do depend. I mean, to put your question slightly differently, see, we considered the leading Einstein-Hilbert action, but you can have all kinds of corrections which goes as r square, r box r to the 4, right? In string theory, or in general, just from the Wilsonian point of view of renormalization group, right? You expect that there will be all kinds of cutoff suppressed terms, that you generically higher dimension operators are always allowed. They will be generated even if you don't add them. And the coefficient in string theory have to be exactly precise to give you exactly precise these B and C's, such that the resulting answer agrees with D of Q, which you can compute by completely different methods. So that's what sort of gives you confidence or some faith in the the framework of string theory, that there is some kind of very extremely tight internal consistency in the theory. You cannot tweak one corner of the theory. Either it completely falls apart or it has to be completely right. And we don't know which one of it is. It could be completely wrong also.
This calculation of coefficients, B, C, etc. They are the ab initio.
Yes, ab initio you can do. Yeah, how can you calculate it? Well, using some methods, so it looks almost impossible. Using supersymmetric localization methods, you can do it. In simpler cases, you can actually for example, this coefficient, you can calculate this coefficient. To calculate this coefficient, what you have to do is that, given a theory, you have some spectrum of particles. Suppose like standard model. So you take all the massless particle in your theory and you calculate their logarithmic determinants, log of the determinant, and that will give you this coefficient. But to calculate the next one, you require much more information. But some of these calculations have been done independently, and they agree. So there is a fair amount of body of literature to tell you that what we are doing is correct.
No, so this is computed by computing what?
So for example,
Start with some actions. What is input to get?
what is the input to do this? So for example, in addition to this theory, you might have some scalar fields in the theory. I mean, in a given string theory compactification, you might have some scalar field. You might have some fermions. And the one loop correction is obtained by just looking at one loop diagrams of all these particles in the black hole background. And it's a bit of a heroic calculation, but you can sit down and just do it. And people have done that calculation, and it agrees with.
That one loop calculation generates.
No. So the one loop calculation will only give you this coefficient.
What about
Yeah. So the other computation you cannot get by doing this kinds of a perturbative analysis, because as I said, even in QED you cannot do it.
I understand. My question is,
How do you do it? Yeah.
S of Q is area. It's a geometrical interpretation.
No, S of Q is area only to the beginning.
Fine, but S of Q, then what is the physical quantity that in the quantum field theory framework, string theory will compute, which will have the interpretation of the first term being
S of Q. Very good question. So let me explain that.
they compute partition function.
Yeah, basically it's a partition function. Yes, it's a good point. So this is related to a calculation of Gibbons and Hawking But basically, you can define a partition function with some appropriate boundary conditions in the presence of a black hole. Okay, normally the partition function has interpretation as free energy. But okay, if you define it inappropriately and in some extremal cases.
That formula,
Yes.
action, path integral, and
Exactly. So therefore, this is a in principle well-defined formula. If you have some number of bosonic and fermionic fields, you're supposed to calculate this. The metric, some bosonic field, some fermionic field.
this is computed with some boundary, this area is given.
Yes. Now, doing the one loop calculation is relatively easy. You can do it directly. But I mean, relatively easy. It still goes over hundreds of pages. But people have done those calculations and they agree with the counting. But to go beyond, what you can do is using the fact that it is actually this path integral is supersymmetric, you can localize the path integral to finite dimensional integral. And that allows you to calculate all these coefficients. So it's and they agree in a rather non-trivial way with the counting problem.
So you need to know this action hyperderivative question.
Yes.
So
How do you know this? Yes. So it turns out that's where supersymmetry comes in an important way, that the action has D terms and F terms. So, for example, if you remember, like if you take the West-Zumino model, right, there are terms like phi dagger phi in terms of the superfield notation, and then there is a superpotential, which is in chiral in superspace. Whereas this is, it has d2 theta and d2 theta bar. So it's not chiral. This is the kinetic term and this is the superpotential. And if you remember, there are non-renormalization theorems for the superpotential, which are not, they don't hold in general. So using the non-renormalization theorem, you can show that these terms are the only ones that contribute to the entropy of the black hole. And therefore, that actually reduces the class of terms that you have to look into enormously in some simple examples. Generically, even those terms are infinite, but in simple cases, they actually become finite and you can calculate everything.
Sorry, here S of Q is action, and there it is entropy.
Sorry, so let me call it I of Q. I. Sorry.
So the solution around which you are doing this calculation, that also has to be correct.
Yes. So it's a
It's an exact calculation, right?
yes. Yeah, but his question is that you cannot do the calculation order by order. I mean, if you do the calculation order by order, what you have to do is that the leading answer is given by the let's say the Reisner-Nordstrom solution. But the Reisner-Nordstrom solution itself gets correction when you add corrections. And it looks almost impossible that you can do it, but it's because of localization that in some cases we have been.
The interpretation of A to be the less than not.
Yes, in the large charge limit, the A is really the area of the vacuum. But for small area, you do not have a simple interpretation of the entropy. So this is,
But
I mean, then the area loses its. Okay.
it has enough mathematical handle to show that it's going to.
Yeah, I mean, you can always be in the limit where, say, area is of the order of 100. I mean, not area, not infinity, but area finite but large.
Yeah, I'm asking that there's enough mathematical handle to show that it's an integer.
Yes. No, that's where the modular forms are going to come, and that's where Ramanujan's work actually comes into picture.
One more question.
Yes, please. Yeah. No, it's good to have questions because I.
Calculate this quantity function approach with getting dependence on Q. Is this computed on manifold boundary? Where is the A coming? The relation between Q and A is coming from where in this calculation?
So, yes, it is on a manifold with a boundary. That the main point is that
A is given in some
yes,
no, so you must put a boundary value so the metric must also something. Otherwise, what is the A?
yeah. So if you look at the Reisner-Nordstrom black hole near horizon. So I wrote down the solution, right? The Reisner-Nordstrom solution. If you look at this solution, if you go near horizon, so this is a quadratic equation in R, which has two solutions. R is equal to R plus and R minus. And R plus is the outer horizon, R minus is the inner horizon. So if you now look at this solution near R plus, near R is equal to R plus, then it's fairly easy to see that this actually is anti de Sitter 2 cross S2. And anti de Sitter space has a boundary. And on that boundary you have to specify some boundary conditions on the fields, which tell you what is the area of the black hole. And the S2 has an area. So
First, like the limit at R plus goes on minus.
yes, yes. So you take some limit appropriately, R plus R minus approaching each other, and R becoming closer to each other, closer to that. In that limit, you get ADS2 cross S2. ADS2 is basically like a disk. So the geometry is very simple. It's the Poincare disk. ADS2 is like a disk, Poincare disk in Euclidean. So Poincare disk, let me remind you, right? If you have, it's like the metric is something like this: dx square plus dy square. I mean, it's dr square plus r square d theta square, 1 minus r square square.
So my question is, so is this path integral evaluation done with the background specified or what is it?
This background.
No, so the background is not specified because you want to integrate.
Evaluation.
Yeah. Yes. So what you can hold fixed, you cannot hold only the boundary. You fix only the boundary data and you allow the metric to have arbitrary fluctuations inside.
So you choose the boundary. On boundary, some of the fields, in the metric field, there you say it has this particular boundary condition.
Yes. Yes.
That's what you fix.
Exactly.
And
Exactly.
then compute the path integral
Exactly.
as exactly as you can.
Exactly.
So if you do that, and that generates.
Exactly. Exactly.
But it is
But
where
the A here is the classical A.
Which A?
A in this form of the metric.
from the metric.
That's the number given. The capital A
Yes.
is the classical number.
Well, in the large area, what I'm saying is that, see, once A, it's like it's a how should I say this? It's like a function, right? Right. A function at large x has some expansion, but the interpretation of that x is area only when x is large. When x becomes small, then it doesn't have any simple interpretation.
So you have SFQ on the left.
Yeah, so A of q, actually what I should write is A of q. So I was going from a semi-classical answer. So area is determined from this formula, you see. When you set m is equal to q, the horizon area is determined entirely in terms of q.
That's classical. So
That's the classical area. Yeah, that's the classical area. So maybe I should call it A classical.
yeah. Okay. That's that.
Yeah, then it's well defined.
It's a particular function of Q which is fixed.
Exactly. It's a particular function of q.
By matching with the
Yes, yes. Yeah, but if you want to do the ab initio calculation, you don't talk about area at all. You just talk about what are the charges of the black hole, what is the mass of the black hole. You hold the Maxwell field and the gravitational field fixed according to those boundary conditions, and then you try to do the path integral.
in that case, given the metric which is fixed on that, I will get a classical area anyway.
Yes.
That area is same as this.
Yeah, to leading order it will agree to this.
And the relation between A and Q is the same.
To leading order.
This thing is that how do you know that this is really right now mass of the black hole?
So it's only,
It's a calculation, one calculation.
yeah, it's a calculation that you will find that A of q that you obtain.
Where A is given by the boundary data.
Yes. No, A is not given by boundary data. Q is the boundary data.
But metric also has something. G
So but you will calculate this quantity, this S of q, by doing this path integral, which you can expand for large charge. So just to give you very concretely, it will start looking like something like 1 upon 4 pi q square plus log of q square. And you check that this is actually the area of the black hole in the large q limit. But this is some very complicated function of q, which when expanded at large q has an interpretation in terms of this kind of an expansion. But otherwise it's a very complicated function of q.
Sorry.
Yeah.
Question still is that your path integration, the integration variable contains a metric.
Yes.
The boundary that you are specifying, all fields boundary values must be specified.
Yes.
Therefore, I have boundary value of the metric on this boundary that you have chosen.
Yes. Correct.
Topology space.
Yes.
From that I calculate an area. So the metric is
Does that calculate?
No, I can.
Area is two boundary.
is the ADS2 boundary.
Is there, no? Otherwise, what is the area? Very who is A?
That defines a large cube.
Huh.
I have a small question. This verification that it is an integer is only for large A.
No, I mean, okay, the point is that you cannot trust this calculation completely, but the point, I will explain this in a moment, but it's actually, you get an integer, you see, because when you have an integer, you see, any integer is infinitely far. What I'm saying is that if I write a number like that, see, this number is still infinitely far from 9, right? You really have to get all the coefficients right to get 9. And that's what happens for an infinite set of integers. So this is quite a non-trivial test of string theory.
Sorry. So this you need the specification of the interior of the black hole for this calculation.
No, you don't, because if you remember, once you go to the Euclidean space, the Schwarzschild black hole also just becomes a cigar geometry. Meaning so if you remember, if you see, you have an interior of a black hole for a Schwarzschild in the Lorentzian signature. What happens is that in the Euclidean, only this contributes. And that's actually how Gibbons and Hawking did this calculation.
So on the left hand side, S of Q is really that, right?
Yes. Yes. Okay, how much time do I have?
Half an hour.
I do have half an hour. Okay. So effectively it becomes 3 lectures. I'm happy. Okay. Yeah, so the question that will really surprise you is that how on earth can you express an integer in this manner? And how do you even know that it is an integer? How can you prove that it is an integer? How can you calculate it, right?
One way is easy, the other way is hard.
Huh?
One way is easy. If the log of that is a real number, it will ask an expansion. Other way around is very non-trivial.
Other way around is a non-trivial thing, exactly. And that's where Ramanujan comes into picture. So I'm particularly happy to be giving today's talk in this Ramanujan auditorium. And in fact, actually, I was asked to write there is going to be an encyclopedia on Ramanujan, and I was asked to write an article on Ramanujan and quantum black holes. Because I have been working with a number theorist in the past 5 years, quite a famous number theorist, Zagier. It turned out that some work that Ramanujan had did on mock modular forms just before he died turns out to have it's exactly the kind of mathematics we needed. And I was just talking to him on a cafe, and he said, yeah, this problem has been solved by my student after 100 years of work. And there is a very beautiful story which I will now try to explain. So Ramanujan actually, modular forms in Ramanujan, let me explain a little bit. So for this article I was thinking, what are the contributions of Ramanujan that are really were important for this work? And there are 3 things actually. So one of Ramanujan's favorite problem one of his famous contributions is what is called as partition of an integer. And it's a very simple problem. The problem is, if I give an integer, right? Suppose I give you 3. How many ways can you write it? How many ways you can partition it? You can write it as 1 plus 1 plus 1 or 2 plus 1. There are 2 ways you can write it. So on. The second problem is what is known as the Hardy-Ramanujan-Rademacher expansion. So this is given an integer n, find number of partitions of an integer. And instead of using integers of the same color, I can use integers of different colors. So for example, red and blue. How many ways can I write 3 as? Then there are more ways, right? You can write it as, so let me denote red by a circle. So you can write this as 1 plus, so this is red, okay? Or I can write this as, or I can also write it as, sorry, like that. and so on, right? There are many ways. And as you increase the number of the colors, it will also increase. Then there is a Hardy-Ramanujan-Rademacher formula. Now those of you which gives an asymptotic formula, an exact formula, analytic formula. For P of n in terms of Bessel functions. And this is the kind of formula that we are after, right? This is called analytic number theory. Okay, this is sort of one of Ramanujan's thing. Analytic number theory means on one side you have an integer, on the other side you have analysis, namely Bessel functions, which are continuous complex valued functions. And a priori, it would be a surprise to you if so there is an exact formula which is known as the Hardy-Ramanujan-Rademacher formula for this P of n, which is an infinite but highly convergent exact expression in terms of Bessel function. And that's exactly what we will use, because in fact later on I will identify P of n with D of n. And I'm going to put an index P24. Okay, 24 means 24 different colors. And then the third is what is known as the mock modular forms, or mock theta functions as Ramanujan called them. So Ramanujan, almost when he was in his deathbed, I think, like his last letter that he wrote to Hardy, saying that, you know, Hardy, I have come across this very beautiful functions. They look almost like modular forms, but they are not really like modular forms, and I don't know what to make of them. And the theory of those modular forms, and he had a lot of very nice properties. Then very eminent mathematicians worked on it for 100 years. Nothing came out of it, and people didn't really understand. What is difficult? You see, modular form is a function which is highly symmetric. Now, it is always easy to specify something which is highly symmetric. But mock modular forms or mock theta functions are almost modular, but not quite modular. So it's always very difficult to say. If I tell you a sphere is easy to specify, right? You can write an equation. But if I tell you that sphere with a bump, right, then it's much harder to specify, because you have to tell me where the bump is, in what sense is it almost a sphere. And that's always very hard. And there is an analogous problem for modular forms, that what he called mock theta functions, and the modern language we call them mock modular forms. So he gave them these functions which had all the properties of modular forms, almost all the properties, but they were not quite modular. And understanding that took almost 100 years, and it's only very recently in the work of Zwegers, who was a student of Don Zagier with whom I collaborated, this problem was finally solved. And our collaboration actually then led to a 150-page paper, which will come out as a book eventually as Cambridge Monographs in Physics. It's a kind of an interesting story where totally different motivations somehow are linked together in a very interesting way. So these are the three things where Ramanujan actually will enter this story. And I will explain to you in the simplest possible example, where to give you some feeling that how it connects to black holes, you know. So I have told you now what are quantum black holes. I still have to tell you what are modular forms, and then I will try to connect the two using Ramanujan's theory of partitions. Okay. So what is a modular form? Modular form it's a function of tau, a holomorphic function of tau, defined on the upper half plane. And which there is a modular group which is basically spatial linear group, two-dimensional matrices, basically with integer coefficients. So ABCD are integers, and the determinant of this matrix is 1. That's why AD minus BC is 1. So it's a special because as the determinant is 1, it's a linear transformations to general linear transformations with integer coefficients. That's called a modular group, and it has this very beautiful property. I mean, it's symmetric in this sense. So basically, after a SL to Z transformation, the function essentially comes back to itself. If k was 0, it would be a modular function. Since k is not 0, it's called a modular form. Okay, so it's almost coming back to itself up to some overall factor which depends on k. And then k is called the weight of the modular form. So it looks like a pretty abstract, but this has turned out to be very fundamental importance in a lot of modern mathematics. I mean, really a lot of, if you like, looked at the proof of Fermat's last theorem, it all depends on modular forms. Langland's program, a lot of many very important developments in modern mathematics really depend on modular forms. So it's a very important branch of mathematics. And what does it have to do with our problem, a priori? So let's look at the problem of partitions of an integer. So as physicists, we will actually, to solve a problem, right, when you want to say count in the microcanonical ensemble, you always go to the canonical ensemble, and because the counting is simpler in the canonical ensemble, and then you do some inverse Laplace transform. Right, so it's always good to have a generating function. Right, if you remember, you always do z of beta is equal to d of n e to the minus beta n. This is usually easy to calculate because d of n means what? You have to calculate all the configurations with some fixed energy. But as you know, this is how we go through the canonical ensemble, that you want to relax that constraint. With the constraint, the counting problem is much harder. So you do that by introducing a notion of a temperature. And then you adjust the temperature such that the average energy is n. And so on. That's how you go from thermodynamics to. But it's actually quite simple. Let me define. Okay, this Q is added just for, it's not so important. I mean, it will become important later on. But if I'm interested in the problem of counting partitions of an integer with 24 different colors, right, a natural partition function to write is this. And I will try to convince you that this is the correct answer. To the power 24, then 1 q to the 2 plus q to the 4 plus q to the 6 to the power 24 times 1 plus q cube and so on. So in general, 1 to the q to the 1 to the n plus q to the 2n plus q to the 3n to the 24. And you just expand it, p of n, p24 of n is the coefficient of Why is that? You see, because suppose I write, let's take 3, right? If you write 3 is equal to 1 plus 1 plus 1, right? It can only come from this term. Just taking a frequency to be n and multiplying it 3 times. But if you want to write this to be 1 plus 2, then it comes from multiplying this and this. Both of them also, if you multiply this with this, you will get a q cube. So you have to keep track, this term plus this term will give you the number of ways you can partition the number 3. But this you will recognize is nothing but the partition function of 24 bosons. So for physicists this is obvious. with frequencies there a frequency q, one frequencies 1, 2, 3, 4 like that. But such bosons with frequencies which are integers basically combined into a string. The oscillations of a string are given by various Fourier modes, and each Fourier mode has frequency 1, frequency 2 in some appropriate units. So this counting problem is exactly the counting problem that you might encounter in string theory. Or if you did a, let me write it you in a manner that you will immediately recognize. This is how you did it in your StatMech course, if you remember. This is nothing but the Bose-Einstein distribution. Which basically is a geometric series, no? So if you write x is equal to e to the minus beta h bar omega, this is just the Bose-Einstein distribution, where the frequency is unit 1 in some appropriate.
So the 24 now is only incidental.
At the moment the 24 is incidental because you can have 24 different colors, but very shortly I will see that the 24 actually are the 24 transverse directions of a string. So this 24, it comes out very naturally. So if you now, therefore you can just sum this. And it's going to be 1 minus q square. Right, so we can write it as 1 upon q, product 1 over. And incidentally, this is a very famous function, again, which made Ramanujan famous. I mean, it goes back to Jacobi and Ramanujan. It's called the discriminant function, but Ramanujan used it for many interesting things, including what is known as Hecke. I mean, so again, Ramanujan was ahead of his time. He discovered all kinds of wonderful properties of this function. Our partition function is 1 upon that. Okay, so it's quite different. And then, so is this clear?
Satish, when you were calculating this, when you got this thing from the gravity side, so it's obvious that if you reduce to such a counting problem, you already knew that it will, from the way you count the degeneracy, it will reduce to this counting problem.
Yes, a priori is not obvious. So I'm going to tell you for which problem it reduces to this.
Why is it he was interested in 24? Ramanujan.
No, Ramanujan actually did it for general, he actually did it for not 24, there was just 1. But actually 24, he was interested in this function also, which I mean, so there is something special about 24. Because it's, yeah, for his own reasons. No, I think as far as partitions was concerned, he was not interested in 24. He was just interested in any, it can be 2, 3, 4, 1, whatever you like. And he had a general formula for that. But it turns out that for 24 there is something special, and actually that something special is also related to what happens in string theory. That, as you know, so this is going to relate to string theory, but let me first relate it to modular forms. With minus 12, if you write q is equal to e to the 2 pi I tau. If you write q is equal to e to the I 2 pi, then z of minus a tau plus b c tau plus d
Sorry. What ZQ is for what? What did you calculate? What is the result?
What I'm calculating, this is a partition function for partitioning an integer into integer of 24 colors, 24 different colors. And q is e to the 2 pi I tau. Now here Q is just a dummy variable. But then you discover, I mean, if you're just a combinatoric person, you would do this. Because then you just multiply. Because you see Q cube, one coefficient will come from here, another coefficient. So the number of ways you can distribute is basically comes from this. But then the non-trivial thing that Ramanujan discovered, that this has a modular properties. And that's what gives him all the power. And there is a very nice scene in the Man Who Knew Infinity. You should see it. There's a famous combinatoric person, McMahon, who was very dismissive of Ramanujan and basically kind of a bit racist, saying that, okay, you go back to Madras or wherever, or something like that. But Ramanujan was able to do like that using his formula, using modular symmetry, calculations which took him days. And that is the power of the modular symmetry. I was trying to extract that piece from I didn't succeed for today's lecture. It's a nice scene.
Why should the modular symmetry appear in the first place?
So it appears in the context of string theory because of conformal invariance.
But in general, in a counting problem like this.
Yes, it's not in the general counting problem, it was a mystery for Ramanujan why it appears.
For 24, we know it should have to.
Yes, or even for 1, I mean, if you have a free boson in 1 plus 1 dimension, it will appear. You'll get modular symmetry because it's a part of diffeomorphism. And yeah, so from a path integral point of view, it's clear that there should be modular symmetry if you're dealing with a conformal field theory. And all these counting problems relate to a conformal field theory in the end. So that's the reason why in string theory it appears.
Basically, if you write d square x by dt square in 4 dimensions, the group which leaves it invariant.
Which group?
Projected group. The definition of that is 24.
Sorry?
If you write d square x by dt square with
This? No, which x?
second derivative of x,
Yes.
and if x has 4 dimensions,
Yes.
then the invariance group of this is a projected transformations.
Yes, correct.
Its dimension is 24.
In 4 dimensions, it's not.
See, you write down Newton's equation, first law,
Okay.
but you take it to be 4 dimensions.
Okay.
In this invariance group, if you want to leave it unchanged, is a projected transformations.
Yes, okay. Okay.
Okay? And the dimension of that is 24.
Okay. Any other question?
There is set of all paths which are there is parameterized by a group whose dimensions.
Okay. Any? Yeah. So, how much time do I have? 10 minutes? Any other question? But now let me try to see, our goal is to really calculate Okay, so basically we have solved the problem of partitions, right? Just take this function, you can put it on a computer and expand it to any, suppose you want partitions of 200. Just expand this function to 200 and then whatever terms that you collect them. But this actually becomes exponentially hard. And that's why McMahon and all these people were very confused. I mean, the theory of partitions was not understood. And I mean, was not so powerful until Ramanujan got into it. Because this is exponentially hard. The P24 of n grows exponentially. So if you put it on a computer, I mean, that's the scene in this Ramanujan's movie. That even for P is equal to 200, n is equal to 200, P24 is something like 3 billion. And then 3 is something billion. If you go to the next one, it grows very rapidly. And in fact, the asymptotics you can calculate, and statistical mechanics people are familiar with this. This is called the Cordy formula. Because if you think of this as this is a partition function of (24) free bosons in 1 + 1 dimensions. on a circle. So basically, if you take a boson moving on a circle of radius 2 pi, the chiral part, with some time, right? So this is your space is just a circle and time is just going like this, like a cylinder. Then if you look at the action, right, the boson will be just del phi square. But the Hamiltonian, so what will you do, right? You will expand the boson. So let me call this x and this, or sigma and tau, or x and t. So phi of x I can just expand in phi n e to the 2 pi I n sigma, right? Sorry, in fact I n sigma. If sigma is going from, or x, sorry. So these are just the oscillations of the string, if you can think about it. The number of times string oscillates as it comes back. And therefore the Hamiltonian is just the n times a n dagger a n. And if you're calculating the partition function trace e to the minus beta h, which I can write it as trace e to the minus qh, q to the power h. That's exactly this partition function, using Bose-Einstein statistics. So from a physics point of view, this is a very natural object. And calculating, and the problem of partitions is also very naturally stated now. You could have 24 bosons which correspond to 24 different colors of the integers, or 24 directions in which the string can oscillate. There are many interpretations of it. But the point is that that's why there is a 24. There is an overall Q which is very important for the modular properties. I won't try to explain it. But up to this factor is some kind of ground state energy. This is the formula that you need to do to expand. If you expand it, what is the question that you're asking? This is the number of ways given a system of 24 bosons in 1 plus 1 dimension. If the total energy is n, and if this, how many ways are there? Because these bosons have different frequencies. One boson has frequency 1, the next one has frequency 2, the third one has frequency 3. Right? So there are so many ways. So this is a completely straightforward statistical mechanical calculation. There is absolutely no mystery about it, right? From a physics point of view. But it is related to all this very beautiful mathematics. And knowing that mathematics actually helps you, because now you have the same problem. You see, if you want to calculate P24 of n for n much bigger than 1, it's very difficult, because if you try to put it on a computer, right, you'll have to actually sit down and enumerate. But for large n is like large energy implies what? If I think of Q as e to the minus beta, or 2 pi minus beta, I think of it as a temperature, beta inverse temperature. Then this is high temperature, right? So this is like n is energy. So we need to go to high temperature. That means beta going to 0, right? T going to infinity. But if beta is going to 0, Q is going to 1. Now that's when you cannot expand this function very well, you see. When Q is going to 1, you are running into all these poles. But the modular property tells you that Z of beta is equal to beta to the minus 12 Z of 1 upon beta. Sorry, Z. Using the modular property, because this is a modular form. So instead of doing a high temperature expansion, you can do a low temperature expansion. Because instead of calculating expansion in beta, using the modular property of the function, you calculate it at low temperature instead of high temperature at. But low temperature asymptotics is easy. That's Q going to 0. And Q going to 0, this is very easy. You just drop all these terms and you're left with Q. And you can do some kind of a saddle point evaluation. It's a very straightforward calculation. And this is how actually Cardy derived this formula. For a conformal field theory, he showed that the D of n or P, more generally, if you have some D of n, conformal field theory of some central charge, it goes as exponential of 2 pi or pi divided by c divided by 6 n. And when c is equal to 24, of a 2D conformal field theory, but free bosons in particular in 2 dimensions are conformal. It's a simple example of a conformal field theory, and their central charge is 24. If you have 24 bosons, you have 24. So if you just put c is equal to 24 in this formula, okay, maybe there's a 2 pi here. And this is the formula that actually Ramanujan derived first. So in fact, Cardy is always embarrassed when he says that it's a Cardy formula. He says no, it goes back to Hardy and Ramanujan. But of course, Ramanujan did much more than that. What Ramanujan did was that once you have this kind of a nice property, very, very symmetric function, he was able to obtain an exact expression for d of n in terms of Bessel functions. And it's a highly convergent, it's not an asymptotic expansion, it's an exact. And that's the function that we actually will use later on. I was mentioning that we will use. I'm not going to discuss this, but that's what has been used in the subsequent explorations of quantum corrections to the black hole entropy. But to just summarize, so your P of 24 of n goes as exponential of 4 pi square root of n. And now you can take the black hole that corresponds. So where is the black hole in this? So far I have not considered a black hole. The point is that in string theory, suppose you are in 4 dimensions and you have a black hole here. But actually there are so many internal dimensions. In string theory it has to live in either 26 dimensions or 10 dimensions. There are different dimensions depending on which theory you are talking about. So there are actually 26 internal dimensions. So there is a string that is, if you look at the internal space, it is wrapping some internal space. Okay. Time is, so it is in 26 dimensions. A string in 25 plus 1 dimensions. Suppose you have a string that is wrapping on one of the dimensions. How many transverse directions does it have? It can oscillate only in the transverse directions. 24. The same magic number that we are talking about, 24. This magic number actually appears in all kinds of contexts of K3, and this was actually the basis of dualities and all kinds of symmetries that were discovered later. So this 24 is actually quite important. But basic point is, the picture is the following, that you have a black hole which internally is really like a little string wrapping in some internal direction and oscillating in so many different ways. And there are 24 transverse bosons running around that string. And therefore that black hole can be in so many different states. And the number of states you can calculate, and its leading answer is 4 pi square root of n. And this agrees, okay, our analog of this agrees with, I will not give all the details, but S of n with precise coefficient. See, it could have happened that you got 2 pi, then the answer would have, the string theory would be wrong. Right? It's highly non-trivial that you get exactly 4 pi square root of n. Or you could have gotten 2 pi n to the power 3 by 2. Right? There was no reason a priori, unless there is some internal consistency to the theory. So this actually is one of the, and what subsequently people have found, in particular our group, I have worked a lot on this. We found that you can actually complete this into an integer by adding all the non-perturbative corrections. So I think I'll stop here.
So usually when you use localization, expansion is usually there's an important fact number of terms. Because there's one loop.
Yes.
Saddle points. Probably you get a lot of saddle points, but for expanding.
No, you just get one single saddle point and one loop around it.
One loop around it.
Yeah. So
here, how does it relate to the expansion?
very good point. No, so that's a very good question. The point about localization is that, suppose you're doing some path integral. So localization is, suppose you're computing this path integral z of q. I will just write it as e to the minus with some boundary condition. phi goes to phi something at the boundary. This is the path integral you want to, which depends on q. Right? This is the problem you want to solve. And there is a saddle point of this. The classical physics is basically a saddle point evaluation of this path integral, right? So where this vanishes, that is Feynman has told us, right? That's the stationary space approximation of the path integral. So that gives you some saddle point at phi is equal to phi classical, which is the analog of the, let's say, the Reisner-Nordström black hole, because my phi now includes also the metric and everything. And then to evaluate this, you have to keep on doing one loop corrections, two loop corrections around the saddle point, as we normally do in quantum field theory, right? You start with some path integral and then you just evaluate it perturbatively. That means that you're evaluating around some saddle point, right? What localization does is that it adds to it some lambda, some other action, let's call it W. And you show that, so there is an h bar sitting here, you see the. So why is the saddle point approximation good? It becomes arbitrarily good when h bar goes small, then it becomes better and better, right? So that's the semi-classical approximation. In localization using supersymmetry, what you can show is that if you add a specific W of phi, then this function is independent of lambda. And your original function is lambda equal to 0, right? Because if you put lambda equal to 0, you get the function that you want to evaluate. But now you say that since it is independent of lambda, let me evaluate it lambda equal to infinity. Then this term is just a small correction. And I do the saddle point evaluation of this. So I have a different saddle point. Let me call it phi localization. And amazingly, the one loop evaluation around that, and there one loop is exact because you can really take lambda go to infinity. Unlike h bar, which is a physical parameter. Since it's just a parameter, you can take lambda strictly to infinity. So one loop approximation is exact. So this is how, just by doing a one loop calculation around a new saddle point, so roughly speaking in field space, right, your phi classical is somewhere here, and this is where you are doing perturbation theory. But phi localization is somewhere here. And amazingly, one loop approximation around that gives you the full exact answer.
And W phi itself has h bar and.
No, it doesn't have h bar.
But as prime. Nothing.
No.
If there are other phi zeros for I phi,
Yes.
if there are more than phi classical.
No. By phi I mean phi I. If I can have infinite.
I'm saying that there seems to be a one-to-one correspondence between the extrema of I and W.
No. Different localization.
Yeah,
It can even be some number of localizing solutions, like some finite number of
no,
them.
how do I know? So suppose I has multiple
Saddle points.
Yeah, saddle points.
Yes.
Where am I doing the calculation?
So typically in classical physics there is a dominant one. In localization actually there can be more than one saddle point. So this actually sometimes is parameterized by some set of parameters, but finite set of parameters. So the power of localization is it reduces a path integral which is infinite dimensional to a finite dimensional integral, which sometimes you can actually do explicitly.
It gives you an answer exact in each bar.
Yeah, and the answer is exact in h bar.
So therefore it should correspond to something or
Exactly. So that's how you are able to get an integer. So otherwise, if you have to do it term by term, in fact, no perturbative expansion ever converges, right? It's known that it's an asymptotic expansion. So you can never recover, but if you do it localization, you get an exact answer. You're not summing a perturbation theory.
this question is it should correspond to all
Yes, I
saddle
understand.
points and all fluctuations around.
Exactly.
So suppose you had saddle points which correspond to multi-centered black holes.
That brings us to mock modular forms, as I will describe next time. No, it's exactly the question that bothered me for a while. And it turns out the answer is mock modular forms as formulated by Ramanujan for this case of black holes.
Okay, so my confusion is still there. So this W of phi doesn't have any G string or alpha prime.
It doesn't have any physical interpretation. It just more or less is determined by supersymmetry transformations.
Yeah, but precisely for this reason that you need infinite number of terms to get an integer, you should have an infinite expansion.
They are all sitting in this I phi.
This infinite expansions.
Yes. So I phi is the infinite Wilsonian action including all higher derivative terms.
This is where the
information about the alpha prime goes in.
Evaluate I on the file localization.
Yes, yeah. You have to evaluate I on phi localization. Exactly right. And then integrate.
That's why it is. And GS corrections, they stop.
They are also included. No, everything is exact. GS is here. G string square is. No, it's exact quantum answer.
You don't get an infinite expansion.
No, you don't, because yeah, it's all. It's a. You'll get a non-trivial answer which is valid for all values of the couplings.
Sorry, W of I is specified if you specify I of I.
No. W of I actually. So there is a bit of an art. So localization has been sort of used a lot lately in various problems in cohomology and so on. Witten actually pioneered this method. It goes back to Atya and people like that. And there is a bit of an art about figuring out what W of I should be. In supersymmetric theories, it's more or less determined by supersymmetric transformations. So if you know the supersymmetry, offshell supersymmetry transformations, then they don't depend on the action. It's like a diffeomorphism transformation, right? The supersymmetry transformation is exactly like I tell you, under diffeomorphism, how does the metric transform, right? I tell you, right, if x mu goes to, this I specify once and for all, and then I can write down all kinds of diffeomorphism invariant actions, right, R square and so on.
So I is invariant by itself.
So I is invariant by itself under off-shell supersymmetry transformations. It's actually quite non-trivial to get off-shell supersymmetry. See, unlike diffeomorphisms, this off-shell supersymmetry is a whole industry, and which I had never paid any attention to. But actually, when you want to do some calculations like that, it's very.
Like W seems completely arbitrary. So what is the
It's not arbitrary, but it's determined by this transformation law.
Could there be two different I's?
Yeah, there are examples where there are two different I's and you get the same answer. You're guaranteed to get the same answer by this logic. If your methods are correct, then you have done the calculation correctly. Then
so the restriction on W you're saying is just diffeomorphism.
no, supersymmetry. I'm taking this as an analogy. So suppose you have some bosonic field.
So sorry, then independent of I have one answer for supersymmetry. Is that what you're saying?
It's not independent of I since you evaluate I on the file localization.
Choice of W.
Choice of W is arbitrary to the extent that suppose I tell you that I is invariant under some supersymmetry. Say epsilon bar psi and delta psi is equal to, say, I don't know, epsilon bar gamma mu del mu phi, something like that, right? Once I specify this, from that I can construct, and if I know that I is invariant under this action, then I can construct W of phi, which depends only on this. So it's pretty simple object, it's does not depend on, you could write down some very complicated action, right? Some arbitrary superpotential.
So any supersymmetric invariant I will have the same answer.
Yes. No, not the same answer, same W.
Same W, and therefore when you do this.
No, but because then you have to evaluate that action.
I think we should just go into this session last time, Manish, again.